In this lecture, we are going to turn our attention to standard regression models involving two variables. The standard regression model is a workhorse in statistical modeling. We're going to take this simple model and expand it to many, many other situations. But the beauty of linear models of these regression models is that the math stays the same, even as they get more and more complex. So at its most simple form, a linear regression involves two variables, an x variable and a y variable, and there's some relationship between the two variables that is linear, right? That is to say, when you plot the data out, you can plot it with a simple line. Linear models make assumptions in order for their corrections, in order for their performance of inference to be correct. And these assumptions can be remembered using the acronym LINE. So the first is linearity. Obviously, a linear model only works if the data are actually linear. Independence, which, as we've talked about, is a subtle and mysterious concept in statistics, but also has some very precise mathematical definitions in terms of linear models, in terms of what happens when you sample over and over again at a given point along one axis. And we'll talk about how we mathematically express this concept of independence in linear models. And we'll also talk about, later in the semester, more sophisticated models that can begin to actually relax some of these assumptions of independence. Normality. And normality in a linear model has a very specific meaning. It means that at each data point, as you sample, like if this is one axis here, as you sample at that data point over and over again, the error that you would get around the model line itself is normally distributed. And there's an assumption of equal variance. So if you sample this data point over and over again here, you get a normal distribution. And that normal distribution has the same variance as the normal distribution here. The mean of the sampling on a linear model is always the linear model itself, the regression line itself, and we'll see that coming up. But the assumption of equal variance means that you get an equal variance no matter where I sample along this line. And we're going to describe this in a fair amount of mathematical detail and look at ways to look at these assumptions, especially of normality and equal variance. So linear models are, I said, they're a workhorse in statistics. They're often the go-to model to use when you have a relationship between two continuous variables. And as an example, really, of the power of linear models, this is one of my favorite papers that was published recently, looking at the variation in cancer risk as a function of total stem cell divisions. This is rather an amazing paper that makes an argument that there is a stochastic risk. Just the longer you're alive, you have more and more cells divide, and these cells accumulate mutations, and those mutations put you at risk for cancer. And to a first approximation, your risk of cancer due to these mutations is, to a first approximation, independent of environmental exposure. Now, that might seem like a remarkable thing to say, but the linear fit here between the lifetime risk for these different cancers. So on the y-axis is your lifetime risk for all of these different cancers. And on the x-axis is the total number of divisions of each one of these different tissues. And what you can see is that this is a linear relationship, right? So the cancers that you get most often are in cells that divide the most often, and the cancers that you get the least often are the cancers that you that divide the least often. And on a log division, on a log axis, this relationship is linear over 5 or 6 orders of magnitude of stem cell divisions. So over your lifetime, these cells maybe only divide 10 million times 10 to the 7th, while these cells are dividing more like 10 billion times 10 to the 13th, or 10 trillion times 10 to the 13th, right? But across these 6 orders of magnitude, there's this linear relationship, right? So and again, what's remarkable about this linear relationship is that this is independent of environmental exposure. So if you dig into these papers, there's actually an argument that something like 2/3 of all the mutations that put you at risk for cancer just happen as stochastic response to cell division that we don't have control of. So all the things like exercise and environmental exposure really control a substantial minority, but still a minority of our cancer risk. And again, the argument for that comes from this nice linear relationship here. You can also see that if we think about our assumptions of equal variance, that's actually a reasonable assumption for this data set as well, right? So the variance seems reasonably equal across these 6 or 7 orders of magnitude of differences in stem cell divisions. So linear models, despite their simplicity, are still very, very central to everything that we do in biology, both because they can capture relationships like this one and because they form a mathematical basis for more complex relationships when we go to allow for expansion beyond two variables and to allow special linear models, which we're going to call mixed linear models, that relax these assumptions of independence. So we are going to use as an example of working through the first set of simple algebra for two variable linear models, this example that comes from the Nieder et al. Applied Linear Statistical Models book. This is just some regression. There's two things that are correlated with each other. It doesn't really matter what they are. I think in the book it's like lot hour, like lot size versus man hours or something like that. It doesn't really matter. Just some very, very tight correlation. You can copy and paste this code directly from your browser into R if you want to recreate this plot. Notice this is a much tighter correlation than we ever see in biology. Like this paper that we just looked at is about as good as it ever gets. In biology, you very rarely see such incredibly tight correlations, but that's fine. That doesn't matter for the math that we're trying to work through. And so we're going to get very used to thinking about the data in terms of this equation. This is, you have your data here, your y data here, you have your x data here. There's going to be this design matrix of beta variables. We'll get to know this very well, and then an error term. Right. So for our simple data here, this is a standard linear regression model that you learned about in your first semester stats class. Your yi data is here. Your b0 term, this is the intercept term. There's a hidden term here, which is that you're multiplying this all by 1 to make everything balance out. So when we look at this in terms of the column vectors that equation represents, this is b0 times 1. Then you have b1, your second coefficient, which is going to be the slope of the relationship that you're interested in, times the actual x data, and then this error term, which makes everything balance out, right? So y1, every single one of these is going to be exactly equal. Y1 is exactly going to equal b0 times 1 plus b1 times x1 plus e1. Y2 is exactly going to equal b0 times 1, b1 times x2 plus e2. We're often going to do inference on that this slope variable, that the relationship is 0, right? That there's no association. So a null hypothesis of no association between the y and the x variables are usually going to involve testing the null hypothesis that this slope equals 0. And again, it's very useful, right? It's very useful in looking at this equation to think about the data in terms of the column vector. So if you filled this in, right, you'd have your y data here, you have your b0, your intercept coefficient here, you have your b1 slope with your data here, and in the error terms, right? So whatever the difference is between this, whatever b1 turns out to be, and b0 turns out to be, this error term is what's not explained by everything that's here. So this model makes a number of assumptions. It's kind of worth going through in a little bit of pedantic detail what those assumptions are. So first of all, like up and down here, the expected value, right? So this is actually showing the y-axis here and the x-axis here. So this is flipped 90 degrees from the way you're used to thinking about this. But the expected value along the y-axis is the regression line. Okay, so if you were to sample an infinite amount anywhere along the x-axis, the expected value is the regression line. That's one of the assumptions of this model, right? So this says this sort of over and over again in this section from the Nieder book, right? The expected value of any particular data point is on the regression line, and the expected value at any y-axis is the regression line. So if you were to sample anywhere along the x-axis, an infinite number of times the expected value is the regression line. And as we indicated in a few slides ago, right, the variance around that expected value is the variance of the model. So that's the sigma squared, and that is constant up and down the regression line, right? So the expected variance is the variance along the regression line, right? So this is going to be a very important idea, that the expected value is the regression line itself, especially when we get to the analysis of variance way of looking at the linear regression, where we're really going to be thinking a lot about like what data can we explain by this expected value versus what are we not able to explain by this expected value of the data along the regression line. Again, so if you sort of to zoom in on this and now rotate it again, so that this is the x-axis and this is the y-axis, right? So looking at it the way you more normally look at a linear model, right? The expected value. So if this is your fit, the expected value is the regression line itself. Notice that is the intercept plus the data. That's b0 times 1 plus b1 times x. The error, right? That's this part here. So this part here is the expected value. The error is what's not explained by the model. It's the distance from the regression line, right? And so that's the distance between the data that you actually observed. Yi is the data that you actually observed versus the expected value. And those yi's are the errors, and those errors are normally distributed with a constant variance. So no matter where you sample up and down this x-axis, those yi's are normally distributed with a constant variance. The variance is the same at this point and that point. And these assumptions of the linear model are going to be important in order for us to have meaningful p-values from the linear model. So there are going to be a number of ways to fit linear models, but the easiest one to understand is approaches that minimize the residual of sum squares. Okay. So we're going to define this as the sum squared errors, right? So this is the sum squared of how far each data point is from the regression line. Mathematically, right, that's the difference between y hat. So this is the first time we're seeing this y hat symbol, but y hat equals the regression line itself. So mathematically, that regression line is equal to the b0 plus b1 part of this, right? So this is the actual model, right? b0 plus b1x. We'll call that y hat. So that's the regression line itself. That's the model line itself, right? And so the error is defined as yi, the data point, minus the regression line itself. And the regression line itself is b0 plus b1x, right? So there's a minus sign there. So the error is yi minus by b0 minus b1x, right? And we can see that mathematically, right? You just solve for ei here. So the error equals yi minus b0 minus b1xi. And so if we sum that across all the possible xy value pairs and square it, that's the residual sum squared, right? So it's the error sum squared. And what it's going to turn out that our linear models do is they're going to find the b0 and b1 values that guarantee that this is at a minimum. Okay, so we're going to be able to very easily find very, very simple calculation for a two-parameter linear regression like this that only has an x and y value. It's very, very simple to find values that minimize the sum squared values of b0 and b1 that minimize this sum squared errors. And so that's the sum squared errors. We're also going to define a mean squared errors, which is just this thing divided by n minus 2, where we lose 2 degrees of freedom, one for our estimate of the intercept and one for our estimate of the slope. So we have residual sum squared errors, or error sum of squares. This is what gets minimized. And then we're also going to define mean square errors, just this thing divided by the appropriate degrees of freedom. So it's super easy in R. So R has this really very nice syntax that makes things very, very easy. So if this is our x data, this is our y data, all we have to type in R is linear model, that's a function, y data, squiggle x. And then if we type summary of my linear model, R is going to dump out all this information. We'll go through this output in a fair amount of detail. But this is the estimate from the residual sum squared. These are the values for x and y. Of course, this data set is chosen so that these values are perfect integers. Most of the time they won't be. So this is the value for b0 and b1 in our model, right? The model for b0 and b1 that minimizes these residual sum squared errors. Okay? And that's what these values are. You can also find these values with very minimal programming, and we'll show how to do that in a minute. The basic idea, right, to derive these, to find these, again, it's not complicated, right? So we write Q, let's just call Q here, equals the sum of yi minus b0 minus b1 xi squared. That's just the sum squared residuals, right? So we want to minimize this Q. And we want to minimize it with respect to b0 and b1. So we just take partial derivatives with respect to b0, b1 and set those to 0. Right? And then it gives us two equations to solve here. And if we graph this is a little bit of Java code. I won't go through this, but it's just a little bit of Java code that actually generates the residual sum squared. So for this data set, that's our example data set from the book. We just get that. So these are the sum squares, right? This is yi, each data point minus b0 plus b1 times x. That's the sum squared. We just get that. And this just shows a three-dimensional plot where we have b0 and b1, different values of b0 and b1. Right? And so this makes a three-dimensional plot. We can sort of think of this bowl that we have. It's this bowl that we have, right? And what we want is the bottom of the bowl. We want to find the values of b0 and b1 that give us the bottom of the bowl, right? That's what it means to set the partials find the partials and set them to 0, right? So we want to find the values of b0 and b1 that minimize this both. That is to say, that minimize the residual sum squares, right? And so we do that by just setting this to 0. We end up with these two equations. And then all we have to do is rearrange these equations, and we get b0 and b1. And again, following the logic here from this very excellent textbook, Applied Linear Statistical Models, by Nieder et al. So this just is simply algebraic rearrangement, and this gives me very, very easy formulas to find b0 and b1. Right. So if I have yi and x, the average of the y data and the average of the x data. So the average of the y data minus b1 times the average of the x data gives us the intercept. How do I find b1? Well, b1 is just the sum of xi minus x average times yi minus y average divided by the sum of xi minus x average squared. Right. So I just rearrange these equations from setting the partial derivatives of 0. b0 and b1 just drop out of that. Right. And so we can code this up in R. Right, so I can just take these equations from the partial derivatives, put them right into R, and get b0 and b1. So I can just type this up. So this is just taking these equations and putting them to R. But of course, much easier thing to do is to say summary linear model y squiggle x. Right, so I can do all of this work, or I can just trust that R has implemented this correctly, and I can get my b0 and b1 intercepts, the values of b0 and b1 for the intercept and the slope that minimize the residual sum squares just from R. So that's all well and good. So now we can also do inference, right? So it's not enough really just to find these intercepts. What we usually want to do is test a null hypothesis, and in fact, usually the null hypothesis that we want to test is that this slope equals 0, right? So if we go back to our original equations here, right? So the question is, this is the slope term, right? And so we want to test this null hypothesis, right? If the slope equals 0, then there's no relationship between y data and x data, right? So if we think about this, right? If we just draw this in Paint, right? So here's a y-axis, and here's here's a y-axis, and here is here's an x-axis that's here, right? And you guys will forgive the differences, right? And I have a bunch of data points that are here, right? So I make a bunch of data points, right? If these are just random data points, right? So I just have a bunch of random data points here. If these are random data points, when I fit a regression line to these random data points, it's going to look like that. Okay, so there's no relationship between y and x. So we say that we're testing an inference that the slope equals 0. But if I have a graph like this, right, where I have lots of data points, maybe I can make these data points a little bit bigger in some way. So well, maybe not. Okay, so but if I have a situation where I have lots of data points, you guys have to use a little bit of imagination on these data points. If I have a situation where the data points look like this, right? And then the regression line looks something like that. The regression line looks something like that, right? The regression line looks something like that. In this case, the regression line here, the null hypothesis is the slope does not equal 0, right? So if you just have random data scattered when you fit a regression line to it, the null hypothesis is that the slope is going to be 0. When you have data points that have a relationship to each other and you fit this b1 parameter, the null hypothesis is that the slope, you'll reject that null hypothesis that the slope equals 0. So you can see here that when we look at this, R is giving us a p-value. This is the p-value that the slope between the x and the y is 0. Now, obviously, when we plot these data out here, right, this is a very, very tight relationship. That slope is clearly not 0, right? So when we fit a regression line to these data, the slope of that regression line is not going to be 0. So we reject, for this made-up data set, the null hypothesis that the slope equals 0 with a really small p-value. So how does R know how to do that inference? How does R know how to calculate this p-value? So we're going to prove something here. So I'm not going to go through this proof in detail. So there's a proof in the Nieder book that you can follow, so you can work your way through this proof. What's going to come out of that of the Nieder book is going, or this proof of the Nieder book is going to be that this value is t distributed with n minus t degrees of freedom. So this defines a standard error of the slope, okay, And that's the mean squared error divided by the sum of x squared minus the sum of xi squared divided by n, right? Remember, this mean squared error is the residual sum squared error divided by n minus 2 from the previous slide, right? So what this proof is going to show us, and again, we're not going to go through that proof in detail, although it's there if you want to follow it. It probably will take you about 10 or 15 minutes to go through if it's of interest to you. Is that the standard error of the if this is the slope that you estimate from the data, and this is some slope that you're testing against, and this is almost always 0, right? So you normally test against the null hypothesis that the slope is 0. You don't have an expectation of what that slope is going to be otherwise, right? So if this is the slope that you're estimating from your model, and this is 0, right? So this slope that you're estimating from the model divided by some standard error of the slope, and the standard error of the slope comes out to this, and the proof that that's the standard error of the slope is here, if you wanted to go through for why that is, that this is t distributed with n minus 2. So when we type this into R, right, so I can take all of these equations and I can just put them into R, and you guys can verify that this is done correctly. So in this first part, I grind through and I get my estimates for B0 and B1, right? And again, doing this right from the data directly, using the equations for the partial derivative set to 0 to find B0 and B1. So in this first part, I find B0 and B1. Once I find B0 and B1, I can calculate the mean squared. The mean squared errors is just the residual error squared divided by n minus 2 from the previous slide, right? So this is just a function of the total error, right? And so I get my mean squared error term by just grinding through that as the error term squared, right? So these are the error terms here that I calculate here. So what's not explained by the model, right? So here's the error term. This is everything that's not explained by the model, and then I just have the sum of the error terms squared, and then I divide that by n minus 2, and that's my mean squared error. Right? And then to get the standard error, I'm going to take that mean squared error, and I'm going to divide that by n minus 2. That's the number of data points, right? Divided by, right? So the error term squared is the residual sum squared divided by n minus 2, right? So that's this top part here, right? So this MSE here is the sum of all the error terms squared divided by n minus 2. That's this top part here, right? And the sum of x squared terms here is from this part here. So I calculated that all the way up here because I knew I was going to need it later, right? So it's the sum of x squared 0. So this is just it's just xi minus xi mean, right? Squared, right? So that's the sum of xi minus x average squared. That's calculated here. The mean squared error divided by the sum of x squared gives me my estimate of the standard error of the slope estimate. Okay, and because this is such an incredibly tight regression, that standard error is really, really small. Okay, so when we plot this out, when we plot this out, right, there's very, very little wobble in this line. So when I make an estimate of the slope, I have very little error in that standard in that estimate. Again, remember that the error involves, right? So we don't have the regression line drawn here, but that regression line is going to be extremely tight. The error involves how far the data points from the regression line. The data points are not very far from the regression line. Right? Because the data points are not very far from the regression line, when I grind through this estimate of the standard error, right, that estimate is very, very small. It's 0.046. If I take the ratio of my estimate of the slope divided by the standard error, that is what I'm going to calculate PT on. So this number, the ratio of the slope divided by the standard error, is this number here. That's the t value that I'm going to evaluate. And I'm going to evaluate that at n minus 2 degrees of freedom. So that's the number of data points that I have minus 2 degrees of freedom. Now this is a two-sided test. My null hypothesis is not that the slope is greater than 0 or less than or equal to 0. It's that it does not equal 0. When I say PT here, that's giving me the cumulative t distribution, but that's only one side. So to get the final p-value, I have to multiply by 2. So when I do that, I get this 1.02 times 10 to the minus 10th that R is giving me as well. So that's a lot of typing. I can do all of that typing, or with much less effort and much less typing and much less chance for error, I can just say linear model y squared equals x and give this, and R will give me the summary. So in this line of the summary, R is giving me an estimate for the slope. It's giving me that so that's this B1 here, this is 0. I'm testing against the null hypothesis that the slope equals 0. That's almost always what we do. This standard error of the estimate of the slope is given by this number. The proof for that is in the Nieder book, two slides previous to this, right? The proof that is in fact the standard error of the slope comes from here. The important part of that proof is not so much you knowing the proof, but that the assumptions that are used to make that proof are normality, equivariance, and independence. So when we say the assumptions of the linear regression are normality, independence, and equivariance, that impacts the p-value. Right? The standard error of the slope relies, the derivation that this value is the standard error of the slope relies on the normality and equivariance assumptions. The regression fits, right? This no matter, even if your data are not linear, even if they're not normally distributed, the regression fits are guaranteed to give you the lowest residual sum squared errors, right? So your regression fit is always going to find the bottom of this parabola, even if you're in violation of the assumptions of normality and equivariance. But if you're in violation of normality, of the assumptions of normality and equivariance, then the assumptions that you use to say that this is the standard error of the t-test are incorrect, and this p-value might not be correct. So the assumptions of independence, the assumptions of normality and equivariance and independence matter for generating the p-value, because those assumptions are used to generate this equation for the standard error. They are not, those assumptions of independence, normality, and equivariance are not required for the guarantee that these estimates of the slope will minimize the residual sum squared error. That will happen no matter what the direction of your data are. So you get a lot for free when you type the summary into R, but it's very helpful to know actually what you're looking at here. Estimate of the slope, B1, standard error of the slope, this equation here. This equation comes from a relatively simple proof with assumptions of independence, normality, and equivariance. The t-value is this number divided by that number. That's the t-value, and then what that proof shows is that this value is t distributed with n-2 degrees of freedom. So if we know the t distribution, we know the sample size, we can change this to a p-value, and that is a p-value for the null hypothesis that the slope equals 0. The residuals are used so frequently, and they're we need them so often for so many different things in linear models, that R has a term directly that will allow you to calculate the residuals directly. So once you have the linear model, you can say residual my linear model, and you'll get back these EIs. These are not squared; these are the raw EIs. If you want the sum squared, you have to calculate it yourself. But that is a much more efficient way to calculate these residuals than what I had to do here, which was actually calculate the difference between the observed data. And so here I calculated yi minus y hat, and I had to sort of tediously do that in a loop. I can get those yi minus y hats directly by just using the residual function in R. So this R will report here. We have this mean squared error. Remember, the mean squared error is the residual sum squared divided by n-2. R will give you the square root of that value, and you get that basically for free as part of this report that's here. And again, this is a measure of how much is not explained by the model. So this value 2.739 is the square root of 7.5, right? So this number relates to this to what the Nieder book calls the mean squared errors by just a square root function. Now we can also do tests against the intercept. So we can test that the mean equals 0, or we can test that the intercept equals 0. R is also reporting a p-value for that. There's a similar line of argument derivation for the intercept, which I haven't shown you. You can go to the Nieder book if you're interested in those derivations. This p-value is not used nearly as often, right? So if you think about a linear regression, let's go all the way back to our biological example, all the way back in the second slide of this lecture, right? So the slope equals 0 is of interest, right? It's an interest that your lifetime risk is related to the total stem cells division. So you can imagine in a linear model for these data set testing that the slope equals 0. The intercept equals 0 says that if the total stem cell divisions equal 0, your lifetime risk also equals 0. That really doesn't make sense. We have to project this down all the way out to the left side of the screen. That really doesn't make very much sense, right? We don't care about that biologically. And so that intercept in biology, the intercept is the inference based on the intercept is used much less frequently than the intercept of the slope. Than the test of the slope. So the test that the intercept equals 0 is used much less frequently than the test that the slope equals 0 in biology. But of course, there's nothing wrong with that test. If for some reason you wanted to test that the intercept was equal to 0, the logic is very similar. And again, you can go to the Nieder book to see see how these numbers are calculated and what the justification for that p-value is. It's the same assumptions: independence, normality, and equal variance. So the same assumptions that guard the p-value for tests that the slope equals 0 guard the statistical test that the intercept equals 0. Finally, we can ask how well does our data meet these assumptions of independence, normality, and equal variance? So we've just argued that if you're doing inference against either the slope equaling 0 or the intercept equaling 0, those p-values are only valid to the extent that your assumptions of linearity, independence, normality, and equal variance are valid. So often you can just look at the data. So you can just plot it out. Right? Clearly, this is linear. Now, there's so little variance here that's actually hard to say is there equal variance. But it isn't as if there's sort of one data point here where there's massive amounts of variance, and then smaller data, and then at other parts of the curve there's less variance. Right? As far as we can tell, the variance appears about equal. And likewise for our biological example here, right? This is clearly a linear relationship, and clearly there's fairly consistent variance across the entire x-axis. So we'd be pretty confident of the p-value here regarding the slope, right? And clearly a statistical test that says that these two values are related is clearly not out of the ballpark because clearly they're related, right? You just look at the data. So there's a lot to be said for just looking at the data as a quick sanity check before you do a linear regression. Does it look as if the data are actually linearly related? And does it look as if there's a reasonably consistent variance across the entire range of the x-axis? R actually has some plots that can help you evaluate this. So you can actually say plot my linear model, and it will give you a series of plots. These plots will test, for example, do the residuals change consistently as a function of the regression line itself. Right? So as you walk up the x-axis, and these are different data sets, but as you walk up the x-axis, do you have consistently higher residuals at one point versus another? So you're looking for a fit that's sort of along this dashed line, because if you have a data set in which the residuals are dependent on the x-axis, right? So if you had a data set where there's way more variance here than here, then by definition you wouldn't have equal variance across the entire x-axis, and you wouldn't be along this line. And the next graph that R shows you when you hit plot is the distribution of the residuals normally defined, right? So this is equivalent to typing the residuals command here. You get these residuals. There's an assumption that these residuals can be described by the normal distribution. So we can test that by plotting against QQ norm. I mean, just like we do for any other distribution of values, we can ask whether they're normally distributed. So here we can basically say, take my residuals of the linear model, and are they normally distributed? And again, we're looking for something that goes along the line, and that if we see that, we can have more confidence that our assumptions are reasonable, and that p-values are reasonable. Again, I think a little bit like the t-test, if you have some violation of the equal variance assumption or some violation of the normality assumption, the linear models are actually fairly robust. They can handle some deviation from the assumptions of normality, some deviation from the assumptions of equal variance. And there's a little bit of an art or judgment about deciding when is too much variation, when is variation from a normal distribution, or such as shown here, or a variation or an assumption of equal variance, such as shown here. When are we so far enough away from those that we should be suspicious of values that we see? And I think in general, I tend to be very suspicious if you have one or two data points that look like they're really driving the relationships. Then I tend to be more suspicious of models that are driven by outliers. Again, there's a little bit of an art to it, and we'll see many examples over the course of the semester where we think we have good fits to linear models and poor fits to linear models. So we'll get some experience about when we should believe the results of linear models in terms of inference and when we should be more suspicious of them. And finally, if you're reading ahead for the next lecture, we're going to be talking next about ANOVA approaches to linear regression and the F-test. So you can read about ANOVA approaches to linear regression and the ANOVA tests in your first semester stats book, or if you're following along in the Nieder textbook, you can progress to the third chapter.